Welcome to the Crazy Head Chemist. So, good morning, good afternoon, and good evening. Here we go, folks, and we are doing another awesome video here. This is let's check it out here, folks. Nuclear chemistry worksheet number 1. This is going to be part 2 because I did part 1 already, and I covered problems 1 through 17 in part 1. This is part 2, and so we will be starting off with problem number 18, I believe. So, before we get started on this, I'm going to cover one other thing that I did cover at the beginning of a last worksheet, or the same worksheet, the first part. So I'm going to cover one more thing here that's going to be critical to this particular worksheet. So I'm going to move these weights here off to the side, cruise on over here, and let's zoom in on some of this information that's going to be critical for us this time here. All right, so here we go. This is some very important mathematical manipulations that you're going to need here today. All right, so we have 3 different methods of determining the half-life. And I will show you all 3 within this video, so you should feel comfortable with all 3 eventually. One of them is the most frequently used one. All right, so here we go. One method of using the half-life and determining the half-life is actually to use kind of like a samurai sword and chop that piece in half repeatedly until you get what you want. Now, that can be really nice and easy for a short number of half-lives, but it is quite tedious and time-consuming. And in addition to that, because you're doing repeated steps over and over again, it's hard to keep track of everything. So it's actually easier to use an alternate equation. This is what the vast majority of students use, and it is this equation here. It's 1/2 to the power of the number of half-lives times the original amount is equal to the amount remaining. So making sure that this power right here is the number of half-lives. It's not the half-life time, it's the number of half-lives. Okay. The second possibility is the integrated first order rate law in conjunction with the half-life equation. And the integrated first order rate law is right here. It is the natural log of x sub t divided by x sub naught is equal to negative kt. Natural log. And x sub t is the amount at time t. X sub naught, x sub 0 is the amount at time frame 0. There's a negative sign there. Don't forget about that. And K is called the rate constant. The rate constant is per unit of time. So it could be per second, could be per minute, could be per day, per hour, whatever it is. T is the total amount of time. What is essential for this equation is the half-life equation. And the half-life equation is T of 1/2. This is the amount of time for the half-life. This T of 1/2 is different than this number of half-lives, 2 different things. This is the natural log of 2, which is actually a number, 0.693, and more decimal values after that. And then K is also the rate constant. So what ties the integrated first order rate law and the half-life equation together is the K, and that is the rate constant. So that is actually critical. All right, so without further ado, let's see if we can hammer through some problems, and I'll show you a couple of different ways. Sometimes I'll show you one way, sometimes I'll show you more than one way for each problem. All right, so let's get it on, baby. Here we go. Half-life problems. We're going to pull this aside. We'll be using that, and we're doing problems 18 through 25 right now. All right. So here we go. Fresh sheet of paper for number 18. All right. Let's put some weights on here so we don't have these pieces of paper fly away. All right, so what we've got here is problem number 18, and it says the following. How much uranium-238 will remain of a 50.0 gram sample after 5 half-lives? Okay, so one way to do this is a table method, okay? And this is the simplest mathematical method that you can potentially use, okay? I don't think it's the simplest method, but I think it's the simplest method for the non-scientist, for the one that is just trying to learn how to do these problems. So table method is the following way. Let me show you that. I'm going to get out a ruler so that we can help assist with this table method. So here we go. It's kind of like making a T-chart is this table method. So that's effectively what I'm doing right here is doing a T-chart. Okay, and on one side is going to be the amount. On the other side here is the number of half-lives. Okay, so it says you start off with a 50-gram sample, and we are going to go through 5 half-lives. So the amount that we start off with is 50 grams. Okay, and at 50 grams, we have not gone through any half-lives. So that is 0 number of half-lives. So what we're going to do is we're going to take our calculator, and we are going to add 1 for every single time that we go through here. And so this will be 1 right here. And then on this side, we are going to be dividing by 2 with our calculator. So 50 divided by 2 is 25, and 0 plus 1 is 1. So these two things correspond. So after 1 half-life, there's 25 grams yet remaining. So let's see if we can continue this process. What we're going to do is add 1 to the previous number. In the column of the number of half-lives, we will have 2 half-lives. And in this column, we're going to take the 25 and divide it by 2, and we will get the number 12.5. Okay, so that's after 2 half-lives. Okay, and then again, we will continue this process of adding 1 on the right-hand column with the number of half-lives and dividing by 2 with the amount that we have, and we will have 6.25 grams at the end of 3 half-lives. So we're going to continue this pattern here until we get to 5 half-lives. This is 4. We're going to divide this 6.25 by 2, and we're going to get 3.125. And it looks like we have 1 more half-life to go through, and we're going to add 1. So this is 5 half-lives. Divide the 3.125 by 2, and I'm going to get 1.5625. Okay, and that's really what we're looking for. We're looking for the number of the amount at 5 half-lives, and here it is. Now, it's not rounded correctly, so we do have to do that. So the 5 half-lives is actually a counting number, so that's an infinite number of significant figures. The 50 grams has 3 significant figures. This is just an isotope, so that has nothing to do with the significant figure. So I have to round this number to 3 significant figures. That will be 1, 2, 3. I'm looking at that 2 for rounding. 1.56, and it's grams, and that would be my answer, the amount remaining after 5 half-lives. Now, I personally find this method to be rather tedious, and I don't like using it. So I'm going to show you an alternate method, which I think is much faster and most certainly mathematically sound as well. We're going to get the same number, but you know, if you're taking a quiz or a test or something like that, then you might want to try both of them so that you get the same number both times. So the other equation is 1/2 to the power of the number of half-lives times the original equals amount remaining. Okay, and so you just need to use this one. This one works very nicely as well. It's a fantastic method, and I personally like this one quite a bit. Most students like this one eventually after they get used to it. So this 1/2 is a constant. The number of half-lives is 5. Remember, that's a counting number, so it's actually an infinite number of significant figures. The original amount is the 50.0 grams, and we're solving for the amount remaining. So it's really simple here. We're going to take 1/2 on our calculator. That's actually 0.5. We're going to take that to the power of 5. We're going to multiply that by 50. And the amount remaining is going to equal 1.5625. And again, we have to round this number. We have 1, 2, 3 significant figures. 1, 2, 3 significant figures. We're rounding with that 2. That's less than 5. We're going to truncate the number. That's 1.56 grams is my answer. And look at that. These two numbers are equivalent to each other. So super simple, super easy. You should be able to get that. Okay. Hopefully that worked out well for you. Remember, I am the Crazy Hat Chemist, and please watch my videos on YouTube and please subscribe to my YouTube channel. I think you'll learn chemistry. This is the right place. You have found the correct place to actually learn real chemistry. This will give you a strong, solid foundation in order for you to be successful in your future courses of chemistry, maybe even at the college level. All right, so let's move on to problem number 19, and we can see how that one flies. All right, so problem number 19. Let's get this problem set up here on the page. We're at the top this time. There we go. All right, let's leave our paperweights on here. Nothing like a little shameless advertisement, the Crazy Hat Chemist. All right, okay, thanks. So here we go. We are going to do problem number 19. It says the half-life of protactinium 234 is 6.70 hours. So that's T of 1/2 is equal to 6.70 hours. How much will remain? That's what we are actually solving for right there. How much will remain of a 100-gram sample? So this is the original amount. And then we have after 26.8 hours. This is the total time. Okay. All right. So let's first get on with the column method. Okay. And we can figure out what we need to do from there. Okay. So that's effectively writing a T-chart. So what's what we're going to do right here, right now. Sorry for the bell, folks. All right, so what we're going to do is a T-chart. And see if we can nail this T-chart. I don't know how many we have to do, but there we go. All right, so on one side of the T-chart is the amount, not unlike what we did before. And then the other side is going to be time. And this is going to be in hours. Okay. And so let's see if we can get this one settled here. So the amount that we are starting off with is 100 grams. That's 100 grams, and there's a decimal at the end of that. And this is at time frame 0. So at time frame 0, you have 100 grams. Okay, and we are looking for at the end of 26.8 hours, how much will remain. So what we're going to have to do with the amount is divide by 2. And then with the time, we are going to add 6.70 hours for every time frame. So we're going to get 50 grams. And over here, we're going to get 6.70 hours. Okay. So this time has not reached the 26.8, so I need to carry on and continue. So this is going to be adding 6.70 hours, and I'm going to divide by 2. And that will be 25 grams, and then a total of 13.4 hours. This 13.4 is not 26.8, so I am not quite done. Again, I'm going to add 6.70 to this column here. I will get 20.1, and then I'm going to divide this by 2, and I will get 12.5. So 20.1 is not equal to 26.8. So I need to continue on. So I'm going to add the 6.70 hours. I will get 26.8. And then I'm going to again divide by 2, and I will get 6.25. And this is grams. So it just so happens that we have finally made it. We have hit the 26.8-hour time frame, and how much will remain is 6.25 grams. I put the units there of grams, and also that is the total time, 26.8 hours. This has gone through, let's see, 1, 2, 3, 4 half-lives. Not really so bad, to be perfectly honest. Okay, so let's see, and this is kind of the beat it with the stick method, hit it with a hammer. You got a samurai sword, slice it in half each time. You just need to know where these numbers are going. So let's do an alternate method on this one as well and see if we can do that one. So the alternate method is 1/2 to the power of the number of half-lives times the original amount is equal to the amount remaining. We did this last time, so that shouldn't be so bad. Again, sorry for the train bell, I'm really close to the train station, so do apologize for that. For those of you who know, that's actually a pretty funny joke. All right. So what we have to do is figure out, we do have the original amount. We have the 1/2 to the power of what? That is the number of half-lives. We don't have that number. We do have the original amount. It's 100 decimal grams. And we are solving for the amount remaining. So we need to solve for that. So let's see what we need to do. We need to acquire the number of half-lives. So to acquire the number of half-lives, this is what we're going to do. We're going to take the total time divided by the half-life time. The total time is 26.8 hours. The half-life time is 6.70 hours. Okay, now you need to make sure that these two are in the same set of units, which are hours. If one's in hours and one's in seconds, you need to convert one into the other. So we're going to do 26.8 divided by the 6.70, and we're going to get 4 half-lives. This number goes right there, which of course goes right here for my power. So now I have my equation. I have 1/2 to the power of 4 times 100 is equal to the amount remaining. And so I'm going to plug this into my calculator. I'm going to get amount remaining is 6.25 grams. That's 3 significant figures, of course, because that decimal at the end of that 0 on the 100 gives me 3 significant figures. And there's my answer. And does that correspond to the previous answer? Of course it does. It most certainly does, right? 6.25 grams, 6.25 grams. Fantastic. All right. So I am going to show you yet one more possibility for this problem here. So we're going to have the same problem, except this time we're going to use the integrated first order rate law and the half-life equation in conjunction with each other. So I've just shown you here 2 different methods. I'm going to show you a third method. So again, it's entirely up to you. If you have the time during an assessment of any kind and you want to make sure that you got the correct answer, well, by all means, you should try as many methods as possible until, of course, you are running out of time. All right, so we have the same problem here. So what we're going to do is we're going to slide this up. So I'm going to do a little folding of this paper here because I am going to try to get just the question here for our problem so that you can see that still. Okay, perfect. So there we go. So you should see that we are doing the same problem. Okay, we have not changed the problem. It says the half-life of protactinium-234 is 6.70 hours. How much will remain of a 100-gram sample after 26.8 hours? So T of 1/2 is equal to natural log of 2 over K. So what we're going to do is we're going to rearrange this equation, right? So this is going to be over 1. We're going to cross multiply, and we are going to solve for K. Hopefully you can do that. K is equal to natural log of 2 over T of 1/2. So what we're going to do is we're going to plug this right into our calculator. That will be natural log of 2. That is a number. Okay, and then we have the half-life, which is 6.70 hours. We're going to get a number here on this, and that is 1.0345. 4803069 times 10 to the negative 1, and this is per hour because it's per unit time. Now, I am not going to round this number because we're going to plug this into the next equation. So here we go. The integrated first order rate law is natural log of x sub t, that's the concentration at time t, divided by the concentration at time 0 is equal to negative kt. So what we're going to do is we are going to figure out what are we solving for. We're solving for how much remains at a certain time. How much remains at a certain time. Perfect. Okay. So this value right here is the rate constant that's going to go into there like that. This 26.8 hours is right there. 26.8 hours. That is the total amount of time. The amount that's original here is 100-gram sample. So I have all the parts except for what I have highlighted for, and that's what we're solving for. Okay, fantastic. So now before I plug in, what we're going to do is do a little bit of mathematical manipulation, and this is coming from your math class. So hold on, unless you're familiar with this from your math class. And one of the rules for natural log, I'll write that here. Natural log of A over B is equal to natural log of A minus the natural log of B. So this right here is coming from your math class. That's a rule with natural log. So I'm going to apply that rule over here. So natural log of x sub t minus natural log of x sub naught is equal to negative kt. All right. So now what we're going to do is we're going to substitute in those numbers for this particular problem here, like what we have. So natural log of x sub t, this is what I'm solving for. Natural log of, well, x sub naught is 100. So natural log of 100 is equal to negative, and then I'm going to put the k in there, 1.0345, and I'm going to put dot, 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 times 10 to the negative 1 per hour, because I'm going to put the whole entire number that's right here, right in there. And then the amount of time is 26.8 hours. That's the total time. You should see that your hours actually cancel out, so that's a good thing. So now what we're going to do is we're going to do our mathematical wizardry, which is actually not really a lot of mathematical wizardry. It's just actually using this in plugging it into your calculator. So we're going to have a natural log of x sub t minus 4.6051 70.18599. That's actually the natural log of 100. Is equal to negative 2.772588722225. Okay, you could actually keep all these numbers in your calculator. Don't really have to write them down. That shouldn't be a problem. What we're going to do is solve for x. So we're going to have to add 4.6051 to both sides. So now we have We have natural log of x sub t is equal to 1.832 58146374. And in order to get rid of this natural log, we're going to take that to the e. So there's a function on your calculator that will allow you to do that. Then we get x sub t. It's the concentration at time t. X sub t is equal to 6.249999, and there's eventually a 5 at the end. We're going to round this to 3 significant figures. That's 1, 2, 3. I'm rounding with that 9. I'm going to add 1 to the preceding digit. X sub t, we're just having just enough space, 6.25 grams. And does that coincide with the previous two answers, with the two previous methods? That is absolutely yes. That is another way of solving that same problem. So I'm trying to give you as many methods as possible to solve these problems, and that would be a nice, fantastic method of solving this problem. All right, now that we've done problem number 19, we're going to head on over to problem number 20, and so let's see if we can hammer that one. All right, fantastic. So slide that one away. Problem number 20. Let's see here, problem number 20. All right, problem number 20, we have the following. And let's see how we're going to do this one here. It says thorium-234 has a half-life. That's T of 1/2 of equal to 24.1 day. How many days? This is what we're solving for right here. How many days? That's an amount of time that we're solving for. Time. Will it take for a 100-gram sample? So I'm starting with a 100-gram sample. That's original. To decay to 12.5 grams remaining. So hopefully that makes sense for you. You got all the little parts here. So now what we have to do is find the right equation to solve for this. So I'm going to show you, real simple method here, and let's give it a try. So real simple method, again, not the method that I prefer, and quite frankly, the method that most students do not prefer as well either, but let's just put it on here for that simple method. You're lacking time on a quiz or something like that, and you're like, oh my God, what do I need to do? So here we go. So simple method potentially would be the amount. So how many days in time it will take. So we got amount, and then we have time in days. Again, this is not my preferred method, but it will most certainly work. So we have 100 grams, and the amount of time in days is 0. That's what we begin with. So what we're going to add is the half-life time, and that is 24.1 days. So this will be 24.1. And then we're going to divide this by 2, and that will be 50. So in 24.1 days, I will have 50 grams remaining. That's not 12.5, so I need to keep on going. So I'm going to add 24.1 days to this, and I will get 48.2 days. Divide this 50 by 2, and I will get 25 grams. The 25 grams does not correspond to the 12.5. No, it certainly does not. So I'm going to have to add 24.1 days again and divide by 2. So when I add 24.1 days, I get 72.3 days, and I have 12.5 grams. So you should see that this 12.5 grams right here, the amount remaining, corresponds to this. And then here is our total amount of time in which it takes. That would be days. Make sure you have units on that. And that would be one method of solving this problem, and it worked perfectly fine. So, all right, fine, not a problem. Let's try another method, and that other method is using the method that most students prefer, to be quite frank. So what we're going to do is we're going to take 1/2 to the power of the number of half-lives. So we do not know the number of half-lives. So we're going to call that X. That X is the number of half-lives. The amount that is originally present is 100 grams, and the amount that is remaining is 12.5 grams. So what we need to do is solve for X. So first, what we're going to do is we're going to divide both sides by 100. I'm going to zoom on out here because I need a little bit more space for this problem to complete it. So here we go. So what we're going to have now is 1/2 to the power of X is equal to 0.125. All right. So now what we need to do is take use of a rule of log base 10. And so what we're going to do is we're going to take the log base 10 of both sides. Okay. So here is the rule for you so that you can be able to apply this. Log base 10. And let's call this AX is equal to X times log base 10 A. So when I multiply by this log base 10, what it enables me to do is pull this power of X out into the front. So that's what we're going to do. We're going to pull this power of X out into the front, and that's going to be critical for our next step. So now we're going to have X times log of 1/2 is equal to log of 0.125. Now, I didn't write log base 10, but it is still log base 10. Your calculator is probably more than likely already in log base 10. So you just have to hit the log button to get this correct. So now this should be a simple mathematical process. This is like X times 2 is equal to 3. And how would you solve this? Well, you're going to divide both sides by 2. So that's what we're going to do here. We're going to divide by log of 1/2 on both sides. And then what we're going to get is X is equal to, I'll write this in blue, log of 0.125 divided by log of 1/2. And what we're going to do is we're going to plug this into our calculator, log of 0.125 divided by log of 1/2. Okay, and you're going to get 3. So this is equal to the number of half-lives. So what we're going to do with this now is we're going to take the number of half-lives, which is 3. We're going to multiply it by the half-life at time, 24.1 day. And we are going to solve for this. And this will be 72.3 days. So how long does it take? 72.3 days. Perfect. Done. Okay, I'm going to show you one other method to do this one here. And so hang on, because this method actually is really nice as well. So I'm going to draw a line in the sand to show an alternate method. And so what we're going to do is we're going to use the integrated first order rate law. T of 1/2 is equal to natural log of 2 over k. And so what we're going to do is rearrange this just like what we did last time and solve for k. So I'm going to fold this over like I did last time so that you can see all the different parts a little bit larger, and that will most certainly be helpful. Okay, hopefully it had the previous ones already written down. You can pause that video and come back to it if necessary anyway. Okay. Because of course you want to be watching these videos as many times as possible, right? And like and subscribe with everything. All right, so here we go. So what we're going to do is we're going to take this and rearrange this for k. So K is equal to natural log of 2 over T of 1/2. T of 1/2 is 24.1 day. So this would be 2.876. 129 times 10 to the negative 2 per day. I actually rounded this number a little bit, and in reality, I probably would not round that number. So that is the number that you get. I leave it in my calculator. Now what we're going to do is we're going to use the integrated first order rate law. Natural log of x sub t over x sub naught is equal to negative kt. And what are we solving for? We are actually solving for t time. So this isn't actually too bad, to be perfectly honest. Natural log x sub t is the amount at time t, which is 12.5 grams. So 12.5 grams. Okay, and then we have the original amount, that's 100 grams, and that's equal to negative K, which we just solved for K, and that's 2.876129. And I actually have that with more decimal places, 37992 times 10 to the negative 2 per day, and times t. That's what we're solving for, is t. So this is really simple. We're going to take the natural log of 12.5 divided by 100. Simple answer right there. Okay. And then we have this number, and we're going to divide this by both sides. So we're going to get t is equal to 72.299999. And we're going to round that to the appropriate number here, and let's put that right here. So that would be 72.3 days. And of course, this is the same answer that you got before. So hopefully you're really happy, and that worked out well for you on that one too. All right, cool, awesome. Let's get moving on to the next problem, which is number 21. All right, folks, so let's see, that's number 20, and what we need to do now is do number 21. So let's see what we can do about problem number 21. All right, number 21 here, what do we have? It says, how much radon 222 will remain of a 10-gram sample after, so this is the original amount, so this is x sub naught, this is original. After 22.8 days, so this is time. The half-life, T of 1/2, is equal to 3.80 days. So this is the half-life. Cool. So let's see what we can do in solving this problem right here. All right, so again, what I will try to do is I will try to do different methods so that it makes sense to you. All right, cool. So what we're going to try out is that beat it with a stick method, my least preferred method, beat it with a stick. I don't like beating things with a stick. So just, you know, it can work. What can I say? So this is the table method, beat it with the stick. Let's see what we come up with this one here. So this is columns. We have the amount. And the amount that we're starting off with is 10.0 grams. And then we have time. And that's in days. Day-o, day-o, day-o. All right. All right, so you can continue the rest of the song if you want. All right, so here we go. What are we going to do? For the amount, we're going to divide this by 2 each and every time. So you would end up with 5 grams. And then the amount of time, we're going to have to add the half-life. So we're going to add 3.80 days. So that's 3.80 days. So It says how much will remain after 22.8 days. Is that 22.8 days? It is certainly not. So I am not done with that then, consequently. So I need to keep on hammering this out. We're going to beat it with a stick again. We're going to add 3.80 days, and we're going to get a total time of 7.60. We're going to divide this side by 2. We're going to get 2.5. Is this 22.8 days? No, it is not. So I need to keep on going. So add 3.80 days, divide this side by 2. I'm going to get 1.25 grams, and over here, I'm going to have 11.4 days. Is 11.4 equal to 22.8? The answer is no, I am not done, sadly. So I'm going to have to add 3.80, divide by 2. I'm going to get 0.625, and then the time now is 15.2. Is 15.2 days equal to 22.8 days? The answer is no. So I am not done. So I'm going to keep on hammering on through this process. Here we go. We're going to add 3.80 days, and we're going to divide by 2. And so what are we going to get? 0.3125, and we're going to get 19.0. Is 19.0 days equal to 22.8 days? Answer, no, we are not done. So I'm going to keep on going. I'm going to add 3.80, and then I am going to divide by 2, and I'm going to get 0.15625, and I'm going to get 22.822. If I could write a 2 there, 22.8 days. Oh my gosh, bingo! 22.8 days equals 22.8 days. How much remains? It's right there. Okay, this is truly beat it with the stick method. I don't really particularly like this method. It's really tedious. It has a lot of chance of making a simple little tiny error along the way. And it could be even where you start off with the 0, or you start off with the 3.8, and then boom, it's all gone and doesn't work anymore. So not my preferred method. Let me show you another method here. The other method is going to say, I want the total time, and I'm going to divide by the number, or I'm going to divide by the half-lives. The total time is 22.8 days. The half-life is 3.8 days. You're going to make sure that these units are the same. They both happen to be in days, so that is good. This is 6 half-lives. So now I'm going to use that other equation right here. Okay, and that other equation is 1/2 to the power of the number of half-lives. The number of half-lives are 6. The original amount is 10.0 grams. Now I'm going to solve for the amount remaining. See how simple this is? This is so much easier. It is not even funny. Okay, so that's why I like this. Many students prefer this method for this same simplicity. So you're going to take 1/2 to the power of 6 times 10, and what number do you get? Amount remaining, 0.15625, and we're going to round this to the appropriate number of significant figures, which I didn't do over here, but that would be 1, 2, 3, and so that's 1, 2, 3. I'm rounding with that 2. Chop or truncate the number. 0.156 grams is what I have. And that is the amount remaining with the proper number of significant figures. Let's put that over here. 1, 2, 3, chop, because that's a 2, 0.156 grams. Boom, answer. Got the answer twice, so that's looking pretty nifty. I like that. Whew, my goodness. All right. So what we're going to do is we're going to try that integrated first order rate law, because again, you need as much practice as possible. And if you're not in this integrated first order rate law problem potential, then, you know, really you should be someday. So make sure that you practice this, because this is actually a very good method. So I'm going to fold this over like I've done before, so that I have this in a larger format, and then we can work from there. All right. Perfecto. All right, so here we go. Larger format. Yeah, here we go. So we've got our problem written down. And so here is our problem. And we're doing the same problem, except we're going to use that integrated first order rate law for the math lover in you. So here we go. We are still solving for the amount at time t. So we're going to do something similar to what we did on a previous problem, actually. So let's see if we can do this one. Natural log. Wait, sorry. We are going to solve for k. So t of 1/2 is equal to natural log of 2 over k, right? So what we're going to do is rearrange this and solve for k. K is equal to natural log of 2 over t of 1/2. So we're going to plug this in. We're going to do natural log of 2 over 3.80 days. And I'm going to write down a truncated version of this value here. It's 1.82407 times 10 to the negative 1 per day. There are more numbers after that 7, and then we can get to that a little bit later. Then we're going to write down that integrated first order rate law. So natural log of x sub t over x sub naught is equal to negative kt. And there was a rule of which we learned mathematically with natural logs, and that's a subtraction. So natural log of x sub t minus natural log of x sub naught is equal to negative kt. So now what we're going to do is we're going to start plugging in numbers. The time is 22.8 days. The rate constant is right there. The amount that we have originally is right there. So we are going to be solving for this right here, the amount at concentration time t. So that's what we don't have. So natural log at concentration at time t minus the natural log of 10.0 is equal to negative 1.82407 152,779 times 10 to the negative 1 per day. And then we need to multiply by the total time, which is 22.8 days. Okay, all right, fantastic. So now what we're going to do is we're going to do our math. We're going to solve for this x sub t. And so we're going to get natural log of x sub t minus natural log of 10 is 2.3025850929 is equal to negative, and then the product of these two numbers, 4.15888308336. And again, what I would recommend is actually just keeping all those numbers in our calculator, and then that way you don't have to mess with it too much. So we're going to add this 2.3025 to both sides. Add 2.3025 to both sides. Just a little bit of algebra. Natural log of x sub t is equal to negative 1.856297999037. And zooming out just a little bit more, what we need to do to solve for this, we need to get rid of that natural log. So we're going to take the e to that, and x sub t, this is going to be our answer, is 0.15624,999, and there's a whole bunch of nines after that, right? And so what we're going to do is we're going to round this answer to 3 significant figures. That's 1, 2, 3. I'm rounding with that 2. I'm going to chop or truncate the number. X sub t is equal to 0.156. We're going to put our units on there. That is grams, and that is the same answer that we got in the other two methods. Fantastic. Okay, hopefully that worked out well for you. This is a really, really useful method. It works for half-lives that are not whole half-lives. And so that would be really important for some of your future potential problems, okay? All right. Sweet. All right, let's see what we can do. We have another problem, number 22, and let's see how far we can get on that one. All right, folks, we're continuing on. Sorry for that long little delay there. I greatly apologize for that, but let's keep on going. It's number 22. A radioactive isotope have a half-life of 14 minutes. So that's T of 1/2 is equal to 14.0 minutes. If you have 5.80 gram sample, so this is X sub 0. This is the original amount. At 6:05 a.m. How much would remain in a certain amount of time? And this is time, this is the total time. Okay, and then what would be the time at the end of 2.10 hours? All right, so what we need to do here is figure out, first of all, how much time has elapsed, because we have our half-life in minutes and we have our total time in hours. So what we're going to do is going to convert our total time into minutes. All right, so we have 2.10 hours, and what we're going to do is we're going to convert this into minutes. So 1 hour is equal to 60 minutes. And so we're going to take 2.10 hours, the hours cancel out, and we are going to say 2.10 times 60 divided by 1, and that's 126 minutes. And from that 126 minutes, then we have the number of hours within this. So we know that 2 hours is equal to 120 minutes. Hopefully you're good with that. All right, and so this is really 2 hours and 6 extra minutes to give our total 126-minute time period. So we can actually figure out what time it will be at the end of the 2.10 hours. It's not 2 hours and 10 minutes. No, it's 2 hours and 1/10 of an hour. So if we start off at 6:05 a.m. and we know that 2 hours is 120 minutes. So we're going to add 2 hours to this, and we're going to add another 6 minutes to that. So that will be 8:11 a.m. will be the ending time of this. Hopefully that makes sense. So we've got that part nailed. Now what we need to do is we need to figure out how much would remain after that amount of time. So how much remains at that time of 2.10 hours. And here's how we're going to do that. Now, we are going to try to do this tabled method again, and it is, to me, long and, oh my gosh, long and painful. But I really would not use the table method on this one in particular. I would actually try a completely different method because this one is too many half-lives. But we'll give it a try. So we have an amount, and then we have the time. And this time is in minutes. I'm going to leave another column over here because later on in this, we are going to do one other thing, and that will be for the next question is actually related to this one. So what do we have to begin with? 5.80 grams. And this is at time 0. Now, we are trying to figure out how much is left at 126 minutes. That is our total time. The half-life is 14 minutes. So what we're going to do is add 14 to this, and that will give us 14. We're going to divide this by 2. That will be 2.90. Well, 14 does not equal the 126. That's what I'm aiming for right now. So I need to keep on going with this table. I'm going to sadly have to zoom on out with this so that it makes more sense. But we're going to add 14 and divide by 2. That dividing by 2 would be 1.45 and then 28. So that is certainly not 126 minutes. So we're going to keep on going. We're going to add 14. We're going to divide by 2. That will be 0.725 and 42 minutes in total. Certainly not the 126 minutes. We're going to add 14. We're going to divide it by 2. We're going to have 0.3625 and 56. And we're going to keep on going with this problem here. Sorry for the bell. I apologize about that, but it is what it is. Okay, and then we are going to continue on this process here. We now are going to add 14. That would be 70 minutes in total. Divide by 2, and we'll get 0.18125. We're not at the 126. We're going to add 14. We're going to divide by 2. We are at the 84-minute time point and an amount of 0.090625. We're going to add 14. We're going to divide by 2. I'm hoping you've seen that this is painful and tedious, and there are faster ways. 98 total minutes and 0.0453125. And then we're going to add 14 again and divide by 2 again. Oh, yes, that's right. And what do we get? 112 minutes. We're getting closer. 0.02265,625. And then we are going to add 14 again. Wait, we added 14, not 4. Add 14 again, and we now finally hit our magic number of the 126 minutes. We are going to divide by 2. This is where we are going to end, and we'll have 0.011328125 grams. And this is what we're looking for. 126 minutes total time. This is the mass that is left after that amount of time. Finally, okay, now what we need to do is we need to solve with the other method. And it's going to be much, much faster. Okay, so that is what's coming up next is we're going to solve for the other method. So let's see if we can do that. Hold on just a moment. All right, folks, let's see if we can pound this out some more. So that was pretty tedious, as you can see, to get this answer. But let's see if we can do this in another way that is actually easier. In my opinion, I always go for the easier route that is mathematically sound. And so we are going to attempt to do that right now. All right. And that would be that we already determined that the total time is 126 minutes. Okay. And so now what we need to do is we're going to take our total time of 126 minutes, and we know the half-life of 14 minutes. So total time divided by half-life time. So the total time is 126 minutes, and the total time is, and the half-life time is 14 minutes. So I'm going to take these two numbers, divide them, and then I'm going to get the number of half-lives. So there's 9 half-lives. All right, so now what we're going to do is use that other equation that we love so much, and that is going to be 1/2 to the power of the number of half-lives, which is 9. The amount that we started out with is 5.80 grams, and then we will solve for the amount remaining. So we're going to plug into our calculator 1/2 to the power of 9 times 5.80, and very quickly we will get the amount remaining at 0.0113 grams. And that is rounded to 3 significant figures because I have 1, 2, 3 significant figures here for that right there. Okay, awesome. And that was so much easier. Like, this is terribly tedious. It does work, but oh my goodness gracious. Okay, all right. Now what we're going to do is we are going to do this the other method, which is, of course, the longer method of the two. All right, sorry for the multiple pauses, but everybody keeps on making announcements at my school, and if they would stop making announcements, we would be good to go. So I'm sure we'll have another announcement here in just a moment to interrupt us some more. But let's see if we can keep on going with this here. Here we go. So we're going to use the integrated first order rate law to solve for the next one. So I hope you've been keeping up with me on the other ones. So let's see what we can do on this one. Okay. Here we go. So we have t of 1/2 is equal to natural log of 2 over k. And we're going to rearrange this and solve for k. So k is equal to natural log of 2 over t of 1/2. This will give me the rate constant. So that's natural log of 2 over 14 minutes. And this is going to equal 4.95, 105, 128. There are some more numbers there, times 10 to the negative 2 per minute. Okay, so this is the rate constant that I just solved for right here. This is K, the rate constant. All right, now what we're going to do is we're going to plug in the rest of the information into the integrated first order rate law. So what we will have is natural log of x sub t over the original amount, which is 5.80 grams, is equal to negative kt. So there is my k, 4.95, 105, 128, 971 times 10 to the negative 2 per minute. And we're going to multiply that by 126 minutes. We have already previously determined that number. All right, so that looks good so far. So now what we need to do is break this up into our two respective parts. And so we're going to have natural log of x sub t minus natural log of 5.80 is equal to negative 6.23. Oh, wait, sorry here. Negative 6.23. If I can write down what I say, that would be good. 832 462 503. Right? So now what we need to do is solve for the natural log of 5.80. So natural log of x sub t minus 1.757. 857. 91755 is equal to negative 6.23. 832 462 503. And we're going to solve this using your fantastic Algebra 1 skills, and that would be adding 1.7578 ... to both sides. 1.7578 to both sides. Draw a line in the sand. I get ln x of t is equal to negative 4.4 H0 4667078. Now what we're going to do is we're going to take e to both sides, and then that would get rid of my natural log, and then I'm just going to have x is equal to 0.013, wait, sorry, 113.28125, and so this is going to round to three significant figures, 1, 2, and 3, and that would be x is equal to 0.0113 grams, and that is your final answer. That's right, and this matches with the previous answers on this problem. Not a problem. Hopefully that makes sense for you. Hey, by the way, a little, self-advertisement, and I don't mind it if I do. And that is, I am the Crazy Hat Chemist, and please subscribe to my YouTube channel. That greatly helps me out. And give me a like, give me a thumbs up. Ask me a question, and I'll answer you. All right. So here we go. We're going to move on to problem number 23. Okay, so 23 is we want to get the percentage. We're actually looking at problem 22, but it says, let's see here. Here we go. Problem 23. Problem 23 says, what percentage remains of the original sample after 126 minutes in the above question? So that was problem 22. So what we're going to do is we're going to pull out what we had worked on before with the previous one, and then we can entertain that answer. Okay, so here we go. So here is our previous one. And so what we need to do is the percent remaining. All right. And so what we have is we're going to do this here. Hopefully this will work out. We have 100% remaining, and that's what the initial amount is. The next one is 50%. Okay, the next one is 25%. The next one is 12.5%. The next one is 6.25%, and the next one is 3.125%. Then the next one is 1.5625%. The next one is 0.78125%. The next one is 0.390625%. And finally, the winner of our chicken dinner here is 0.1953125%. This is actually the answer. It's not been rounded correctly. I'll round this correctly in the other mathematical solutions. So how am I getting these answers? Well, what you do is you divide by 2, divide by 2, divide by 2, divide by 2 until you get to the part that you want. So I'm using the data table to acquire that one. That one shouldn't be all that bad. All right. So now what we're going to do is we're going to answer this same question, but using the other methods. So one other method that I find the easiest, which is this one right here. And instead of starting off with 5.8 grams, I'm going to start off with 100% right here, and then I'm going to get the percentage remaining. So I'm going to write that right down here. I'll do this here in a different color. 1/2 to the power of 9, that's the number of half-lives. 100% is what we're starting off with, equals the amount remaining. So we are going to solve for R in this case, and let's see if we could do that. R is going to equal 0.195%. And that is our answer, and that is rounded to three significant figures, and yes, it does match that answer. Let's see if we can do it with the integrated first order rate law. We had done that one before too. We had a bunch of work on this, and we're going to be using something similar to that. We're going to be using some of the same numbers that we had used before. So I'm going to write that right down on here, and then hopefully that will make this process rather simple and easy. Okay, so we have natural log of x sub t over natural log of 100%. So that's what goes there is equal to negative, and we accumulated, or excuse me, we calculated and acquired the k value already. That's 4.95, 105. 128,971 times 10 to the negative 2 per minute. And we also calculated or determined the 126 minutes, and that was the amount of time in total. And now what we're going to do is we're going to do solving for x sub t here, minus natural log of 100% is equal to a number negative 6.2382462503. That's the same number that we calculated before, natural log of x sub t, minus 4.6051701859 is equal to negative 6.2383246503. What we're going to do is add 4.605, etc., to both sides. Natural log of x sub t is equal to negative 1.63315443904. And now what we need to do is take this to E, and let me zoom on out just a little bit so you can see all of this here. Focus, hocus pocus. There we go. X is equal to 1.95312500002 times 10 to the negative 1. And well, this is actually a percentage already, and that would be x is equal to 0.195%. Look at that. It is the same number that we calculated in the previous problem. So hopefully that is like rockin' solid. Okay, now we are on to problem number 24. We are moving right along here to problem number 24. Okay, number 24, we are one away from the final, and that is 25. I'm thinking that we can do this here, folks. Hang on, don't go away. Let's see here, another little shameless advertisement. I am the Crazy Hat Chemist, so please subscribe to my YouTube video, like and subscribe and all that kind of good flavory stuff. Greatly appreciate it. Yes, that's right, folks. Okay, here we go. Uranium is an alpha emitter. What is the half-life? So I'm solving for T of 1/2. I don't know what that is. What is the half-life? If a 22-gram sample of a nucleotide decays to this number in this total amount of time, that's 955,000 years. All right, so let's see if we can do this. So again, what I'm going to do is I'm going to do 3 different methods on this, and hopefully that will satisfy your needs for every single problem here. Okay, all your needs and desires, etc. Okay, so amount, number of half-lives. So you start off with 22.0 grams, and that's 0 half-lives. So what I need to do is I need to take this number and I am going to divide it by 2. And then I am going to add 1 in this column. Okay, that will get me 11 grams and 1 half-life. I'm going to continue this process until I end here at the bottom. I'm going to end here at the bottom somewhere with this number right here. That's what I'm shooting and aiming for right now. Okay. So I'm going to add 1. That will be 2 half-lives. I'm going to divide by 2. That will be 5.50. Okay. I'm going to add 1 and divide by 2. And so I now have 2.75 and 3. I'm still not at 0.03, 0.34375. I'm going to add 1. I'm going to divide by 2. I'm going to get 1.375 and 4 half-lives. Going to add 1. I'm going to divide by 2. I'm going to get 5 half-lives and 0.6875. And I am going to add 1, and I'm going to get 6 half-lives and divide by 2, and I'm going to get 0.34375. All right, fantastic. So this tells me the mass, which corresponds to this mass right there. Okay, and how many half-lives did that take? That took 6 half-lives. So the total time is 955,000 years, right? It takes 6 half-lives. So if that's the case, then I need to figure out what the interval is. So if I take this and I divide by 6, 159 and 166,007 I'm going to round this to 3 significant figures, so that would be 159,000 years is the t of 1/2. That is the half-life. That is the answer. All right. Oh, cool. All right, so now what we're going to do is we're going to try to attempt to do this problem via another alternate method, because that's what we like to do around here. I like to give you as many possibilities so that you can solve these problems as efficiently as possible for whatever method you feel is the best method, whatever that is. Okay, so here is our next method here. So the alternate method would be 1/2 to the power of x. The original amount is 22.0 grams, and the amount remaining would be 0.034375 grams. And I need to solve for x. So if you remember from before, first thing we're going to do is divide by the 22. That will give us 1/2 of x is equal to 0.015625. Now what we need to do, we need to pull this x out in the front. In order to do that, we're going to take log of base 10 of both sides. That will enable us to pull out this x term. So now it's x times log of 1/2 equals log of 0.015625. Perfect. Now what we're going to do is we are solving for x. So let me zoom this out just a little bit more so we can finish up this problem on this one single page here. All right, so now what we need to do is divide both sides by log of 1/2. Log of 1/2. And so now what we get is x is equal to log of 0.015625 divided by log of 0.5, that's 1/2. This will equal a number, and that number is 6. This is equal to the number of half-lives. So now what we're going to do is we're going to do the same thing that we did in the previous problem here. Okay, and let me make sure that's focused. There we go. We're going to do this the same thing that we did in the previous problem. And what did we do to get that? We took the total time divided by the number of half-lives, and we get the 159,166 and 7/10. We're going to round that to 3 significant figures, so that's 159,000 is years, is the half-life, and that is the same answer that we got on the previous problem, on the previous setup and work problem. Not too bad on that at all. Okay, cool. All right, let's try one more way of doing this. So let's fold this up here and so that we can answer this problem in the alternate last and final third method. And let's see what comes about with that one. Give myself enough space here, hopefully. All right. Sweetness. And let's zoom in on this here a bit, okay? All right, so we're going to use the integrated first order rate law. A little shameless advertisement. I am the Crazy Hat Chemist, and please subscribe to my YouTube channel if you're finding this informative and learning something. And then also, beyond subscribing, give me a thumbs up with a like. So I'd greatly appreciate that. So using the integrated first order rate law, we're going to do natural log, and we have 0.34375 is the amount remaining. The original amount was 22 grams. So I have both of those. I'm going to solve for K. The total time is 955,000 years. So what we're going to do is natural log of, we're going to divide these two. We're going to solve for K, and K is going to equal, we're going to divide by that number right there. And K is going to equal 4.35485139619 times 10 to the negative 6 per year. Okay. Now what we're going to do is do one small thing. T of 1/2 is equal to natural log of 2 over K. So natural log of 2 over this K value, that's 4.35485139619 times 10 to the negative 6 per year. And I am going to plug this in, natural log of 2 divided by this number, and that is 159,166.666 and more. And we're going to round up to three significant figures, 159,000 years. No way. We got the same answer that we got in the other method. That's truly amazing. So that's one of the amazing things about these problems is that you can actually solve it via different methods and you get the same answer. That means that they are all mathematically sound. Now we only have one more problem to do, so hold on to your hats, because I'm the Crazy Hat Chemist. Hold on to your hats, and we are going to continue on and do the next problem, which is problem number 25. So here we go. Whew. All right, folks, we are almost there. So the very last problem is right here. So let's see if we can nail this one down tightly. So here we go. It says how much of a sample of cesium-137 must have been present originally after 270 years. This is the time right there, 270 years. 15.0 grams remains. So this is the amount remaining. And then the half-life is 30 years. So T of 1/2 is equal to 30 years. All right, so golly, we have a lot to do here on this one. So let's see if we can do it. So let's see, 25, it says I'm going to go for that table method since that seems to be a method that some students like to use. I'm not too fond of it personally, but let's give it a try. All right, so let's see what we can do here. So we're going to draw a table. And here we go. Boom. All right, I'm not sure if we're going to need all that, but here's the amount. And then this is the time in years. Okay, so what's critical about this problem is that we have a remaining amount of 15 grams. So this is how much remains. And that is after a time of 270 years, right? Okay, so what we need to do is we need to figure out how much was originally there. So what we're going to do is we're going to go backwards on this, unlike what we have done on previous problems, okay? So we're going to go backwards. So what we're going to do is we're going to go from here to here, and from time, in terms of the time, we are going to subtract 30 years, okay? So 270 minus 30 is 240 years. And then what we're going to do is we want to figure out what was originally there. So we're going to have to multiply this by 2 instead of halving it, like dividing by 2 or multiplying by half. So we're going to multiply this by 2. That would be 30 grams. So, well, we need to get to the point where we get to 0 years is what we're trying to figure out. So how much was originally present? That's what we're looking for. How much of a sample must have been originally present. That's what we're looking for. So let's go for the next one. That's minus 30 years and multiplying by 2. So we should get 60 and 210 respectively on both of those. We'll just keep on going. Minus 30 and times by 2, that's 120 and 180. We're obviously not at 0, so we're not there yet. So minus 30 and times 2. So we did the 120, and let's see, that would be 240, and this would be 150. Okay, so let's keep on going and see what we got. We're going to minus 30 and multiply by 2. So that would be 480 and 120. We're decreasing our time, which is a good thing. That's what we're looking for here. And then so we're going to minus 30 and multiply by 2 again. That's 960 and 90. All right, fantastic. Keep on going, minus 30 and multiply by 2. That's 1920 and 60. And so we got to keep on going because we're not at, we're getting closer here. I can feel it almost. So we're going to subtract 30. We're going to multiply by 2. We're going to get 3840. And this would be 30. Oh my gosh, we are almost there. Let me zoom out just a little bit more so we can get this all in on one page. We're going to subtract 30. Well, now we're going to hit time frame 0. That's the important part. We're going to multiply by 2 and we get 7680 grams. Bingo. Once we hit that time frame of years of 0, that would be the original amount. How much was originally present? 7,680 grams. Fantastic. And that is actually written at 3 significant figures. All right. So that is one method, and hopefully that worked for you. Well, let's give another method a try as well, because that seems to be like hitting it with a stick, which I really don't prefer. Okay, so what we're going to do is we're going to take the total time divided by the half-life time. The total time is 270 years, and the half-life time is 30 years. And from this, we are going to get the number of half-lives, which is 9 half-lives. From this, we're going to use our 1/2 to the power of the number of half-lives. Remember, this 9 right there is the number of half-lives, not how long a half-life takes. Okay, we are solving for this original amount, which would be X, and the how much was remaining is 15 grams. So, piece of cake, folks. 1/2 of 9, 1/2 to the power of 9. We're going to plug that into our calculator. We're going to get 0.001953125 times X is equal to 15. And it's simple here. We're going to divide both sides by 0.001953125. 0.001953125, and X is going to equal 7,680, and that is grams. And lo and behold, that is right there. Bingo, answer. Oh my gosh, wasn't that so much easier than doing the table method? Really, I find the table method to be maybe a useful alternate method in a pinch, maybe you don't know exactly what you're doing, but certainly this other mathematical relationship is so much better. All right. So now what we're going to do is we're going to do this same problem using the integrated first order rate law. And then I'm going to show you that we can get the same number, that's 7,680 grams as the original amount. So let's fold this over so that we can see just this one problem here without getting muddled in the rest. All right. All right, folks, we are almost there. We are almost home free. I can feel it now. That's right. Here we go. Here we go. Still doing number 25, and we're going to do the integrated first order rate law process. Okay. So what we want to do is we want to solve for k. So remember that t of 1/2 is equal to natural log of 2 over k. So what we're going to do is we're going to rearrange this and solve for k. K is equal to natural log of 2 over t of 1/2. Now I'm going to substitute into here. I'm going to have natural log of 2 divided by t of 1/2. The half-life is 30 years. And then I'm going to plug this into my calculator. I'm going to get a number. That will be 2.31049,060,187 times 10 to the negative 2. That's per year. Okay, so now I have k. Now we're going to use the integrated first order rate law, and that is natural log of time amount at concentration T, amount at concentration naught is equal to negative KT. So I'm going to substitute into this equation right here. So I'm going to have natural log. X at time T is the 15 grams. That's what's remaining. I am solving for the concentration at time 0, the original amount, okay, and negative k, that is this value that we just came up with, 2.31049060187 times 10 to the negative 2 per year. And then the total amount of time, that is 270 years. Okay, notice that the years do cancel out. That's really important. We're going to take this here and we're going to do what we need to do. And that is natural log of 15 minus natural log of x sub naught is equal to this number. So I'm going to take this number times that number. I got a negative in front. There's my negative. And this will be 6.238. 324 62505. All right, perfect. All right, now what we're going to do is we're going to solve for the natural log of 15. That's going to equal a number. And so we're going to get the natural log of 15. That's 2.7080. 502011 minus natural log x sub naught is equal to this other number, negative 6.23832462505. It's much easier when you don't have to read it off your calculator, isn't it? All right. Now what we're going to do is we're going to subtract this value on both sides, minus 2.708 and all the numbers therein, minus 2.708 and all the numbers therein. Draw a line in the sand, negative ln x. Whoops, that was an x, not a 0. X sub naught is equal to, and we got to figure out what this number is. This is negative 8.946. 374 82 615. All right, I'm going to zoom on out just to make sure that I can get this whole problem here all at once. All right, now what we're going to do is we're going to multiply both sides by -1. So -1 and -1, and then that will get rid of this negative sign and that negative sign. So now we have natural log of x sub naught is equal to this positive number. I'm going to take the e to that, e to this. Remember, that's positive. Okay. Now I'm going to get x is equal to, okay, here we go. X is equal to what? X is equal to 7,680.000. Oh my gosh, there's a bunch of zeros and eventually a 6, but we're going to round this to 3 significant figures. So we're going to have 7,680. And what is this? Grams. Those are my units. That has 3 significant figures. There's my final answer, and that most certainly coincides with the previous answer that we got via the other 2 methods. We are done. I can't emphasize enough that try these problems with each of the different methods so that you have an idea of what's going on. All right, give it a try. It's worth it. Learn some new math. Now, remember, I am the crazy hat chemist where you get all your chemistry needs met. This is where you need to go. So please subscribe to my YouTube channel. I would greatly appreciate it. Give me a thumbs up. If you actually learned something on this video, then please give me a thumbs up. There we go. I hope you have a great afternoon, great evening, and a great morning. I'll see you next time for more cool chemistry problems. See you next time. Bye for now.